Hi everyone, before we can move on with this idea of slopes of tangent lines or instantaneous rates of change, we need a little bit of notation. So we're going to get into the idea of limits. Limits are a big deal and there's lots of interesting stuff that you can look at with them. We just specifically want to know how to use the notation and be really clear on what it's doing and what it means. So I'm going to give you kind of a working definition here. So this is the idea of what I mean when I talk about a limit. So we've got this notation piece, and we read that as the limit as x approaches c of f of x equals L. What we're saying there is that f gets really close, closer and closer to c, this x value right here. So x is approaching, x is getting very, very close, infinitely close to c. Our f of x or our y values get really, really close to L. And basically, if we were going to do this really formally and prove that a certain value is the limit, the argument would be no matter how close you want me to get my y values to L, say you want them to be within 1/1,000,000th of L, whatever that value is, I can do it. I can find an interval of x's, like a little domain that will fall into that little range around your y values. If f doesn't approach a single value, then we just say that the limit does not exist. So there are actually quite a few situations where we will have limits not existing. So watch for that one. D and E is going to be your friend on some of these as well. The really, really, really important distinction to make here is that f of c, so this is the y value at c, doesn't necessarily have any relationship to the limit as x approaches c. And we'll do an example here so you can see. I think graphical understanding is your very best tool for figuring this out. But I can already ask you, what is the y value when x equals c? That's what f of c means. What I want to know is what's happening very nearby, but not right at. So do not interpret this as asking for f of c. We've already got that. The only new thing here is this thinking about really close instead of right at. Okay, so while we're at it, I'm going to also do a little piecewise functions review here. So I'm going to actually draw these with you. We want to sketch f of x, and f of x is made up of 4 different parts. So the first part is a cosine graph whenever x is negative. So everywhere to the left of the y-axis, we should see the graph of y equals cosine x. I'm going to put an open circle because there's no equal to here. So cosine should drop down from there. It should cross the axis, head to its minimum, and come back up to its top at negative 2 pi, which is negative 6.28-ish. That's slightly off our grid, so let's do pi. Pi is about 3.14, so negative 3.14 would be the minimum. And that should be roughly there. So it's going to come down, it's going to cross, it's going to hit a minimum, it's going to head back up, and then it should be just about up to its maximum. So this is what's happening, and then it'll repeat that, but that's what fits on my grid. The next piece of this function, I'm going to do colors, but this is all one function, so just so that you can see it. When x equals 0, the function equals 2, so that's just a single point, 0, 2. That just fills in the circle, so there is no open circle. It is now a closed circle. The next piece, f of x equals 3 minus x between 0 and 3. Okay, so at x equals 0, if I plug that in, I get 3, and that gets an open circle. The slope, it's a linear function. The slope is negative 1, so I'm going to drop down with a slope of negative 1 until I hit x equals 3, and it turns out that I hit 3, 0, also with an open circle because there are no equal to's there. And then last piece here is 1 over x minus 3. So that's a transformation of our 1 over x function. I have shifted it to the right 3. So that vertical asymptote that was at x equals 0 is now at x equals 3, right where we just put our open circle. And then the function will go like this. I did mentally follow thinking that that would go through 1, 1, so this should go through 4, 1, but that's really the only specific point that I made sure I hit. You can always plug in some numbers to get a few more points, but this is a pretty good sketch. So again, I used different colors just so that you could see what went with what, but this is a single function. This is a piecewise function. Okay, so that's some review on how we get these functions. Now let's look at evaluating some limits. I'm going to zoom a little so you can see this. Okay, so first question, what is the limit as x goes to negative pi? Negative pi puts me right at this minimum. So this is where people get some confusion about the very, very close to negative pi versus right at negative pi. If your function is continuous, then there's no distinction. The value when you plug in negative pi is the same value that you're approaching as your x's are very close to negative pi. So this is negative pi negative 1. That's not what the question asked. It asked what are these y values nearby really close to? But the answer is that they're going to be really close to negative 1. They're just a little bit above negative 1. They're getting closer and closer to negative 1 as our x's get closer and closer to negative pi. Make sure you are thinking about both sides. Limits are always a both sides question unless they say otherwise, which I'll talk about in just a second. Next question, what is the limit as x approaches 0? So as x gets really close to 0 on the left-hand side, my y values are getting really close to 1, the closed circle. If I move to the right-hand side, as my x's get closer and closer to 0, my y's are getting closer and closer to 3. If the two sides don't approach the same y value, that's automatically a does not exist. So if there is any sort of jump in your graph, it's not going to have a limit value. Okay, so I'm introducing this plus minus notation. Now, those are like exponents. This is 0 with a plus almost in the power. This is a one-sided limit. So this means from the right, whereas this one means from the left. So if you see this, this is the only time when you don't have to look at both sides. We can talk about one-sided limits, and we will, mostly as a graphical thing. But I do want you to understand that notation. So if we look at 0 now only from the right side, so coming from the big positive numbers, that's this piece right here that we were looking at. And we said that our y values were getting very, very close to 3. If we now look only at the left-hand side, so coming from the big negative numbers, working our way in when we start getting really close to 0, our y's were getting really close to 1. So if the problem asks you for a one-side limit, give that answer. If it doesn't, this would be a does not exist. Okay, and one more interesting spot. Let's investigate what's happening near x equals 3. So I'm going to do that in light blue. As x approaches 3, 3 is our vertical asymptote. So we're going to have to think carefully about that. As I come in from the left-hand side, my y values are getting really close to 0. I don't care at all that that's an open circle. That does not affect the limit. The limit isn't asking what's happening when x equals 3. It's asking what's happening when x is very slightly smaller and very slightly bigger than 3. As I approach from the right-hand side, my y values are skyrocketing. I have a vertical asymptote, so they are shooting off to positive infinity. So this is a does not exist. Okay, so once again, when you hit those does not exist, you may sometimes be asked for a one-sided limit, or you may even be asked for a one-sided limit without even being asked for the two-sided limit. So let's look exclusively at the left and exclusively at the right. So with the negative sign, that again is from the left. We're going to start on the left-hand side of the graph, and we're going to think about what happens as we get really, really close to x equals 3. And what happens is that our y values get very, very close to 0. On the right-hand side, as x gets really, really close to 3, our y values get very, very large. So we're going to say infinity. I do want to point out that I have seen calculus textbooks and web sources and all sorts of places that disagree on this. Some people will say does not exist because you can't get to infinity. My take on this is a limit isn't about getting there, it's about approaching. So I will actually say infinity if it goes to infinity, negative infinity if it goes to negative infinity. But just if you're out peeking around and you see sources that say otherwise, yes, it's true. There is some disagreement on this issue. Not a huge thing to get super worried about. For the purposes of this class, go ahead and say infinity when it's infinite. All right, so this is graphically the way we want to think about limits.